Okay, so today's review is going to be on current electricity. So we're talking about circuits. So we can't talk about circuits without addressing Ohm's law. So if we originally plotted I versus V, since we know that that's V, since we know that V equals IR, what we can figure out from here is that if I rearrange this equation and solve for I over R, I end up seeing, I over V, I end up seeing that that is equal to 1 over R. So if I look at a graph that is linear, then I know that since the slope is equal to the I over V, that is equal to the inverse of the resistance. So if I really find the ratio of V to I at any particular point, what I end up seeing is that that value for the resistance, or in this case 1 over the resistance, is going to stay the constant. So therefore we can say that the resistance is constant. Now this is a very special case. What we say is that this device, whatever that device is ohmic. And an ohmic resistance, or resistor, all that means is that ratio of V to I stays constant. Well, that also means that we can have devices that are non-ohmic. And a light bulb, for example, since as a filament warms up, it gets warmer, or turns on, it gets warmer, and since that temperature goes up, and we know that resistance and temperature have this relationship, that as temperature goes up, the resistance goes up, then that means that if I take a look at a light bulb, well, its resistance is going to go up, and since the slope is the inverse of the resistance, if R goes up, then that means the slope goes down. So I might see something like this for a light bulb, where it starts off at a very steep slope and gets smaller and smaller as time goes on, which means that the resistance is getting larger. So this we call non-ohmic. So a light bulb is a classic non-ohmic device. So we also know that we have Kirchhoff's rules for circuits, but I guess I'll just remind you of the EMF and then the internal resistance, which is given by the symbol little r, as opposed to the terminal voltage. Okay, so the terminal voltage, if I connect a voltmeter between two ends, a power supply is not a perfect, it doesn't have zero resistance. So if there's the EMF of the battery, and there's some current flow to some other device in the circuit, some big R, then that terminal voltage would be, not VI, the terminal voltage would be the EMF of what started off with, epsilon naught, sorry, I'm a little off today, it is the EMF minus that I times little r. So this is the relationship between the terminal voltage. Now, unless it tells you that the battery has some internal resistance, the EMF is the terminal voltage, and you don't have to factor in that little R times I. Okay, so, well, why do electrons move in the first place? Well, we're going to come back to the parallel plate, and if I hook that up to some EMF source, so there's some EMF, and let's say the internal resistance is 0, and I hook up that parallel plate, well, what's going to happen is that those electrons are going to be forced to move from one side to the other. And since this is the negative side of the battery, that's the positive side of the battery, what we're going to end up doing is we're going to make electrons move through the circuit and deposit on one side of the plates. And so that means we're stripping electrons off of this top plate, making it positive, and we're depositing electrons on the bottom plate, which sets up a capacitor. And that capacitance is calculated by taking the K value, which is the dielectric constant of the material between here, and if we assume it's either air or a vacuum, we have a value of 1.00 times epsilon naught, just some number, multiplied by the area of those plates, so how big they are, divided by the distance between the two. So what we can see is that as the area goes up, so basically we're introducing more space to that capacitor, and to hold that charge, to store that charge, and as the distance between the two goes up, we see that the capacitance goes down. The ability to store charge basically makes it harder for it to move through the circuit. And then we also have another relationship, that the potential difference between these two plates is going to be how much charge was transferred or stored divided by the capacitance. Okay, so these are two relationships in your reference tables that relate capacitance with other variables in the equation. And then we can also really talk about the potential energy that we store. So that is equal to 1/2 Q times delta V, which is equal to 1/2, there's always this 1/2 factor in here, C times delta V squared. And if we plug Q over C, this is actually not in your reference tables, but it's useful to do. What we see is we get Q squared over C squared, but one of those C's are going to cancel out, so we end up getting 1/2 times Q squared over C. And so we can calculate the potential energy that's stored in that capacitor in a variety of different ways. Now, resistors in series and parallel we did a lot with, so I'm not going to talk too much about that, but what I will talk about is capacitors in parallel and capacitors in series. So we have a battery source, we hook up a few capacitors to that battery source, and they're wired in parallel. What's going on? Well, what we know is that whatever that EMF of that battery is, eventually sometime later these capacitors are going to have the same EMF. And we also know that if we talk about charge, if you think about charge like current, well, the current that's initially going on, let's call this I1 and then I2, well, the currents are going to add up to I3, the I total. So we can also talk about the charge, that the charge stored in a parallel circuit is equal to the sum of the individual charges. So that's the Q3 equals Q3 equals Q1 plus Q2. But what we can do, so this is Q1 plus Q2 plus da 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 da. And since we know that delta V equals Q over C, I could rearrange this to be Q equals delta V times C. And if I substitute this in for each one of these, what we end up seeing is we have delta V total times C of a parallel circuit equals delta V1 C1 plus delta V2 C2 plus da 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 da. And it's a parallel circuit where we said the EMFs are all the same, so those delta V's are all the same, and we end up with the relationship for capacitance in parallel. Now you have that in your reference table, so you just add them up. So capacitors in parallel, you just add up. Well, capacitors in series, you have to do a little bit more complex math, which is not too bad. It's the sum, it's the inverse of the sum of the inverses. So we take the individual resistors, we add up the inverses, and then we invert that number, we get a value. So these are two relationships, not that big of a deal, but what I want to focus on is how to solve a capacitor circuit. So for resistors, we set up a VIRP chart. For capacitors, you don't want to do a VIRP, you want to do a QC delta V. And then we could write C1, C2, and C total. Okay, or if there's 3 of them, add 3 in the total. And this is a nice way to store your information, to organize your information. So if I was dealing with a parallel circuit and the battery's voltage is 12 volts, well, I know that when the capacitors are fully charged, they'll each have 12 volts. And let's say, once again, they're a parallel circuit, and the capacitance of each of them is 10 microfarads and 20 microfarads. If they're in parallel, then I simply do a straight sum. So I have a total capacitance of 30 microfarads. And then if I wanted to find the Q would be equal to the potential difference times the capacitance, and that would be of the circuit. We are a little short on time. I'm going to do a second video to follow up with this that deals with RC circuits, and I'll just give you a few pointers when solving them. All right, so thank you very much for listening. Stay tuned for the second video. Bye-bye.